Wavefront shaping through an optical fiber is a cutting-edge technique used to manipulate light as it propagates through complex and disordered media. This process enables precise control over the light's phase and amplitude, allowing it to achieve desired outcomes despite the challenges posed by the medium. When light travels through an optical multimode fiber, it undergoes scattering and mode mixing. This distorts the wavefront, leading to an unpredictable and scrambled output known as a speckle pattern. This loss of coherence is problematic in many fields. In microscopy, for example, it limits how deep organisms can be analyzed because biological tissues act in similar ways as a multimode fiber. To counteract this, wavefront shaping techniques are employed to pre-adjust the light entering the fiber so that the output meets specific requirements. This is a setup similar to what can be expected in most wavefront shaping experiments. A laser source produces a beam that goes through lenses, a mirror, a polarizer, and a beam splitter before encountering a spatial light modulator, which will send the light back into the circuit to enter the multimode fiber before ending up on a camera. We use a spatial light modulator, or SLM, to dynamically shape the wavefront of the input light. The incoming beam that falls onto the SLM will be divided into segments. We can externally apply voltage to each of these segments that will allow the SLM to cycle the phase of the incoming light from 0 to 2 pi before redirecting this modulated light through the fiber. The according output of the fiber throughout this process will be analyzed and assessed by an algorithm that can then compute the optimal input wavefront. This information is then passed on to the SLM, which knows what phase to apply to each segment to achieve this focal spot. Wavefront shaping has transformative potential in various applications, including high-resolution imaging through scattering media and in medical diagnostics and treatments where precise light delivery is critical. This technology exemplifies the intersection of optical physics, advanced computation, and material science, opening new frontiers in manipulating light for practical applications.